So I'm very pleased to be able to introduce this morning's distinguished lecturer, who is Professor Don Farley. Don Farley is responsible for the careers of a number of people in our community, not least my own. Rich Benke once told me that Don Farley's CV is unlike any CV you'll ever see, because there's no assistant this or associate that. Don completed his graduate work at Cornell. He had a NATO fellowship at Cambridge. Not too many people in the room, I think, have NATO fellowships. He spent some time working in Sweden, but pretty much his first real job was director of the Hikamarka Radio Observatory. And after that, his next job was basically a full professor at Cornell University, which is probably a pretty good way to do it. And along the way, he's an IEEE fellow. He received the Appleton Prize from Mercy, and he received a gold medal from the Department of Commerce, something probably there aren't too many of in the world. I really love working my way over to Don's building and talking with him about the early days of radio science and incoherent scatter, when every observation was a discovery, when every piece of apparatus was something you probably built yourself, and where you couldn't check your results against the plasma physics textbooks because they hadn't been written yet. And so I'm really looking forward to hearing what Don's going to have to say. And so congratulations, Don.
Okay, well, thanks for that very nice introduction, Dave. And actually, when I went to Hikamarka, I wasn't the director, but about 3 years later I was. So, hey. So I've got a lot of things to go through today, and I hope I'll get through most of them. Let me start with, oh yes, how do I click? Yes. So basically, I'm aiming this for a general audience. I'm assuming a reasonable fraction of people in here, have heard of incoherent scatter, but they may not be anything like experts. So I'll try to be fairly general, and I promise to have very few equations. What I'm trying to do is basically paint a picture of the early days, basically, and the adventure and the excitement and of the genesis of incoherent scatter radar by some young guys. And I apologize for the fact that they were all guys. In those days, we didn't have very many women scientists, and everybody was under 40 years old. I guess the oldest was Ken Bowles, and he might have been just about 40 when this all got going. So, as an outline, I'll talk about Gordon's first ideas, and then Bowles' first observations and the implications of that for the theory, and then the development of a proper scattering theory. And as Dave said, this had to be proper plasma theory, and there wasn't a whole lot known about plasma theory in those days, so we sort of had to invent it as we went along. And then I'll show a lot of pictures of the construction of Hikamarka and Arecibo, and some comments and stories insofar as I have time. There's some pretty interesting stories, but some of which have never been written down. And then I'll look at some of the early science done mostly at Hikamarka, because that's what I'm most familiar with. And then an important thing is some key aspects of the radar gathering techniques. You think, oh, well, you point a radar, you receive the signal, you do something good, and you analyze it. Well, it turns out that's not so easy with a distributed target. And in the early days, only analog techniques were available, and in the late 50s. And to do proper processing, it's not easy, except unless you have a bistatic radar, which I'll talk about very briefly. What you do is you have to make use of the fact that the power spectrum is the Fourier transform. The power spectrum is a Fourier transform of the autocorrelation function, but then you have to have some digital device, basically, that allows you to do this. And there weren't a whole lot of digital devices around in the late 50s. And the first radar controller correlator device was built went to Peru in the early 1963. It was built in laboratories in Boulder, and it was a remarkably powerful device for its era. And this turned out to be crucially important in making the measurements. And a similar device was added to Arecibo in the late 1960s by John Hagen, who was my first graduate student at Cornell. And we said, look, we've got to shape up the Arecibo data processing. And that was a site, there were some political struggles connected with that. But anyway, we finally did it. And this led to all sorts of fancy techniques that are now used at Arecibo, and some of them are used at Jicamarca as well. Just a few personal notes. I was a grad student at Cornell, and I heard the first really informal talk by Bill Gordon in about April 1958 proposing the incoherent scatter idea, incoherent scatter radar idea. And then about a month later, Bill gave a formal seminar at Cornell expanding on that idea. But I think I'm the only person in the room who was there at the very, very, very beginning and also recently attended two 50th anniversaries, the 50th anniversary of Jicamarca and the 50th anniversary of Arecibo. So I've really, I'm getting long in the tooth, I guess. I've been involved with this for a long time. And I worked on the plasma theory during some postdocs at Cambridge in England and then at Chalmers University in Sweden. And in 1961, I met Ken Bowles at a conference, and he invited me to join him in Peru, where he was building the Jicamarca Observatory, and I thought that sounded like a fun thing to do. So, and it was, as I said, it was. So I went to Peru and stayed there for 6 years, and then and here, as I said, I just recently attended the 50th anniversary of the two, still the two biggest observatories, incoherent scatter observatories. And some more background. In the 1950s, Bill Gordon and Henry Booker, who was my PhD advisor, were working on over-the-horizon scatter communications, mainly for military applications. And first in the troposphere, and in one of my early teaching classes at Cornell, I had a grad student. He was a grad student at that point, and he'd been in the Marines in Vietnam, and he was saying, "Oh, that's what we were doing. They were using forward scatter to get out of the jungle and back and over the near mountains and so on." And he had some harrowing stories about being in Khe Sanh and all these, serious places. And then the idea was, okay, extend it to the stratosphere because you can have longer links possible, like the DEW line, and the Canadian DEW line radars could communicate via this. And then the idea came up, what about the ionosphere? And maybe you could use free electrons. And Bill Gordon became interested in this possibility in the late 1950s. So the idea here, just sketched out, this is the early days ideas of Booker and Gordon, where you scattered from fluctuations in the troposphere or the stratosphere, the dielectric constant fluctuations, and you use it for forward scatter. And then Bill Gordon started thinking about, well, what about using scatter from the ionosphere? And he quickly convinced himself that was no good for communications. But then he said, well, what about using it for probing? Because in those days, there was no way to look above the maximum in the electron density distribution, whereas this would work. The idea is you transmit well above the maximum plasma frequency ionosphere, and the pulses would go through, but they would weakly scatter back. And the question is, so he decided to pursue that. And and this is some more background. In 1952, people were planning for the IGY, and in fact, some of the people like Ken Bowles, in fact, were involved in some IGY experiments, so they knew about Peru. They'd been down there in the early 50s. And in 57, during the IGY, the situation was there were about 75 ionosounds, and in the military were concerned about ballistic missiles in the ionosphere and the ionized trails and whether you could see those. And then Sputnik 1 and 2 went up, and there was lots of money available, which was nice, because military money was available for looking at anything related to all this. And then in 58, there was the Van Allen belts were explored, and ARPA, the Advanced Research Project Agency, military agency, was formed to coordinate and sponsor military programs, and they were interested in promoting radar technology, and that turned out to be very useful, particularly for Arecibo. And so then there was one weekend in Dryden, and some of you, if you've ever been to Ithaca, Dryden is a little town outside of Ithaca where Bill lived, and I'm hypothesizing that it was a lousy spring day, so he had nothing better to do but sit around and think about scattering. So he pondered. And then he thought, well, what about scatter from free electrons in the ionosphere? I mean, really free, independent, because if you're way above the plasma frequency, the electrons ought to be just independent, and therefore the powers would add. So, and he worked out, he rediscovered the fact that who was it, that Thomson worked out back in 1900, whenever it was. But anyway, he revived the fact that the radar scattering cross-section was approximately, well, pretty accurately, 1 times 10 to the minus 28 square meters, which isn't real big. So, but then you think, well, okay, you've got a lot of electrons in the ionosphere, so you get a typical max of 10 to the 12th electrons per cubic meter, say, in the F region. And supposing we think about 10 cubic kilometers, which would be something 10 kilometers in thickness and maybe 1 kilometer across in the beam. And if you add, and you're going to add the powers, not the voltages, because the electrons are completely independent, then the cross-section of all these put together would be 10 to the minus 28 times 10 to the 12 times 10 to the 10th, or 10 to the minus 6, which still isn't really big. This is like a pencil dot, and you know, I can't make a dot anywhere near small enough on the screen. I'm a real honest-to-God pencil dot. And we're going to be looking at this, it's going to be 300 kilometers away. Well, that's obviously ridiculous. I mean, why even think about it? Looking at a pencil dot at a range of 300 kilometers. But, so surely this is ridiculous, and you should crumple up the piece of paper and pitch it. But is it? The question is. And there are pictures of Bill. There's an early picture in 1963, and there's a really nice, relatively recent picture of not too many years ago that I really like. Anyway, that's Bill Gordon. And, well, did I skip one? Yeah, okay. I was back here saying, can you really not detect that? And so this is just continuing. Gordon's monstrous, huge contribution to our field was to actually do this simple calculation. It's easy to do. I mean, it's literally a back-of-the-envelope calculation, provided you know a little bit about available powers and so on. So he did that. And he found that a target, that 1 millimeter target 300 kilometers away, could be detected using 1958 radar technology. And he said, well, so we picked an antenna. He said, well, let's take a nice round number, a 1,000-foot diameter dish, and you work it out, and you take a modern in 58 transmitter of a few megawatts and a 1,000-foot antenna, and lo and behold, you can detect it. And so this was, anyway, I like this quote, so I think it comes up at least one more time. So one Bill has been quoted saying, if you dream, don't be afraid to dream big. And it was his recent advice to graduate students not too many years ago. So anyway, he carried on, and this got talked about. No, I'm not skipping anything. It got talked about, and but two important questions arise. And anyway, there was discussions at Cornell about, you know, should you really do this? And so some questions that arise. Is the scattering really incoherent? Are the electron positions completely uncorrelated? And what about the electron motions and associated Doppler shifts? And how would these affect any scatter communications? Well, you quickly can deduce that it's going to mess up any attempt at scatter communications because you're spreading out the signals too much, because the electrons are moving fast at 100 kilometers per second or so and giving big Doppler shifts. And then, of course, this bandwidth will have an effect on the scattered noise, on the received noise. But Gordon thought at that point that they were truly independent, as long as the radar wavelength was greater than smaller than the electron mean free path, which is the case in the F region and upper E region. But developed in a few months that Ken Bowles, who was a former graduate student at Cornell, about 3 or 4 years ahead of me, but I didn't know him at Cornell, but I met him later. And so he made some very crude observations and showed that Gordon was wrong, and that the bandwidth was much narrower than Gordon had predicted. And so somehow or other, the ions mattered, even though they don't scatter the radar pulses. I mean, you know, the scattering cross-section of ions is virtually zero. It's too heavy. But somehow the Doppler shifts were characteristic of the ions, not the electrons. And what turns out that what matters is the Debye length, which is a few millimeters in the F region. That's a plasma parameter. And compared to the radar wavelength, not the mean free path. So what about these Doppler shifts? Well, if you work out the velocities, the kind of Doppler spread you might expect at 400 at a frequency of 400 megahertz, say, was about 400 kilohertz or so, or give or take a factor of 2. And then so for Bohl's experiment, that would have been he did some experiments at 41 megahertz that we'll hear about in a minute. I'll show you in a minute. So that would have been about 40 kilohertz, but he found it was much less than that. And then you have to worry about convolving the natural, so to speak, bandwidth with the bandwidth of any pulse that you transmit, and that could be a major consideration. Anyway, the frequency spreading would make communications impossible. Probing the ionosphere would be okay, and if you're transmitting it well above the plasma frequency, these pulses will travel up through the ionosphere, and you can look at the top side and the bottom side. In those days, nobody knew anything about the top side, and because you got as far as an ionosound would take you, and that was it. And so the idea of probing up above the peak was very attractive. So anyway, so he showed that it was substantially less than 30 kilohertz, and later there were slightly more accurate measurements, but it was more than an order of magnitude smaller than Gordon's first prediction. So lots of people, including me, concluded that the ions must play a key role, and so we started working on the theory, or looking around for ideas, basically, since none of us knew much about plasmas. And but it turns out, to leap ahead, that for truly incoherent scatter, the radar must be less than the Debye length, which is very seldom the case. The Debye length, again, is in millimeters or centimeters. So anyway, most of the plasma theory details were given in the next few years by papers by Jules Fair. That's not Bella, and no relation, as far as I know, to Bella Fair. And then myself and John Doherty, working in Cambridge, and Tor Hagfors, Ed Saltpeter at Cornell, and a year or two later, Rosenbluth and Rostocker did. I mean, they were real plasma physicists, and they finally got interested and did the same thing. But all of these papers, well, almost all of the papers that were published, arrived at exactly the same results, not just more or less, using very different mathematics. There were a few people who got it wrong, but most people got it right. Now I want to look at a little bit of the data, and notice the dates on some of the slides, the next few slides, keeping in mind that Gordon first conceived of the basic idea in the spring of 1958. And things move incredibly fast after that. This is from the proceedings of the IRE, then, not the IEEE, was then the Institute of Radio Engineers. And this paper was, where's the date here? Anyway, this was published in November 1958. And Gordon's first thoughts about all of this were in April 1958, and the first seminar was in May 1958. And so this whole thing was worked out and published in something like 6 months from the date of the Cornell seminar. And then in 1960 through 1963, what was then called the Arecibo Ionospheric Observatory was built. And along the way, Gordon raised something like the order of $10 million without too much trouble. Well, I guess he worked pretty hard at it, but he raised $10 million or so. And then the inauguration was in November '63 with Bill as the director of Arecibo. And then there were Ken Bohl's first observations that I already mentioned, but he was a former grad student at Cornell, a few years ahead of me. And he heard about Gordon's work in the summer of 1958. He'd been sort of thinking about these ideas himself, but he heard about what Gordon did. And he was working for what was then the Central Radio Propagation Lab, which is now NOAA in Boulder, and had access to a powerful 41 megahertz transmitter, which was in Illinois. And so he contacted an Ithaca tree surgeon that he knew, who had done some antenna rigging for Cornell. And this tree surgeon underbid all the antenna companies by a factor of 3 or so. And he quickly got in his pickup truck and drove out to Illinois with 1 or 2 of his buddies, I guess, and built a 1024 dipole array for this transmitter in a few weeks. So he threw it all together and got it working in a few weeks. Because Ken Bowles happened to know this guy and said, you know, these antenna companies are going to rob me, and what could you do? And so he said, oh, yeah, I could do that for, I don't know, forget what the number is. It's lost, because I went to ask the tree surgeon, but he had died about 3 or 4 months before I thought to ask him, unfortunately. But it was like, you know, a few tens of K, like $10,000 or $20,000, something like that, I think. That's my guess. And that's the only picture I've been able to find of that antenna. It's taken out of it's a reproduction. It's originally from a newspaper and, you know, photocopied and all that. But anyway, these are the dipoles. And this is the only picture I've been able to find of with some scribbling in the corner here, of the original antenna, which is, you know, 4 acres of antenna and so on. So, and this paper, notice this paper was published in December 1958, and there's a story I'll tell you in a minute about this particular date. But these were the first echoes that turned out to be incoherent scatter from this Illinois radar. And so the way you analyze the data basically is you sort of draw a line, literally a line, and measure with a ruler these amplitudes, and then you square them, and then you put in an R-squared factor, and lo and behold, it looks like an ionosphere profile. But this all happened very, very quickly. And these were the first observations on the 22nd of October, and this was actually published in the Physical Review letters less than 2 months later, which is, again, kind of amazing. You think with modern technology we'd go faster, but no. I mean, it was things moved a lot faster in those days sometimes than they do now. And plus, they all had to raise a lot of money for these things too. Oh, well, this is my story of the 22nd. So there was an ERSI meeting at Penn State on that date, and Gordon was presenting his paper that was published a few weeks later at an afternoon session, and he began by saying, I'm going to describe a new way of probing the ionosphere, and then I'm going to tell you about a telephone conversation I just had. And that conversation was with Ken Bowles, and this was on October 22nd, and from the previous slide, that was dated October 22nd. So it turned out that Ken Bowles had told that Bill he was going to try to make some observations that morning, and so Bill called up Ken and said, you know, how did it go? And Ken said, well, yes, I observed it. So it was kind of a dramatic end to Bill's presentation. Well, that's a picture of Ken Bowles back in the 60s, and this is him, well, a few years ago, but basically he's still around. And here was a little bit later, well, not too much later. These were the first indication of the frequency spectrum, because here was some amplitude data taken with a 9 kilohertz filter centered on the transmitted frequency. And here he shifted the filter up by 15 kilohertz, and the echo goes completely away. Here he shifted it down by 15 kilohertz, the echo goes completely away. So the conclusion is that the bandwidth has to be, you know, significantly smaller than 30 kilohertz, because the pulse that he transmitted was about 8 kilohertz wide, so you have to convolve that and so on. So the bandwidth must have been less than, I don't know, 20 kilohertz or 25 kilohertz, something like that. And, you know, way less than Gordon predicted. And then later, this was a confirmation in paper 1960 by Pineo et al., who made some measurements using the Millstone Hill radar, and they also got and that was at 440 megahertz, but they got a spectrum that was, I can't quite, but anyway, tens of kilohertz, several tens of kilohertz wide. Anyway, it was narrow. Oops. What's the matter? Why isn't it going? What's happened? Well, I guess.
You know what you got to do? If you got, oh.
Here's page up and page down. It's not doing it. Oh, okay, there we go. Anyway, I didn't hit it hard enough. And this was a power measurement made by Bowles, and again with that Illinois radar. And here's a profile. So what you do is, this was an output of an oscilloscope, and you basically draw a line there for the noise level, and you measure with a ruler how high these things go, and then you take out the R² factors measuring from here, and lo and behold, you get a curve that looked like that. So this was done in the early days at Hikamarka, when with only a smallish transmitter and a fraction of the final array size. So with maybe a quarter of the antenna and a transmitter with about 10 or 20% of the eventual transmitter power. So anyway, so that we showed that the getting back to the theory, that the simple theory of Gordon's was wrong, and somehow the ions had to matter. The slow ions were affecting it, even though it was the fast electrons doing the scattering, because they clearly had to do the scattering, but and the mean free path is long, so what's going on? And Bowles made some suggestions, but they weren't really, they were too qualitative, and so you really needed a proper kinetic theory. And so those people who were interested in this problem sort of barged in, and using whatever math we happen to be familiar with, and some people did it from a nuclear physics point of view, and you know, I went in with an electrical engineering point of view, and most of us got the right answer with one or two exceptions who shall remain nameless. One of them was a colleague of mine as a grad student at Cornell, and he got it wrong. But he insisted that he was right, and that was bad. Didn't help his career. But so anyway, I was a postdoc at Cambridge at the time, and I shared an office in the Cavendish lab with a advanced English grad student whose name was John Doherty, and he and I got interested in it, and we said, well, let's see what we can do. And so we asked around for the lab for ideas, and some visitor whose name I can't remember pointed us toward a couple of papers by Callan and Welton that had generalized Nyquist's classic 1928 paper, which is a paper everybody should read if they want to read a really classic paper. It's very short. It's about 4 pages, hardly an equation in it, and it comes up with this monumentally important idea. Anyway, the Callan and Welton point out that this idea could be generalized and applied to many problems. And so I had an engineering physics background, and it seemed like an appealing way to go from the Nyquist noise to plasma oscillations. And so the idea is you do a Nyquist thought experiment. You apply a fictitious force to the charged particles, and you calculate what's happening. What happens, keeping all the thermal motion effects in mind, so that the particles themselves see Doppler shifted forces. That's the key concept. So then you wind up with a complex conductivity or an equivalent complex dielectric constant. You plug that into the theorem, and the theorem does all the rest. It does the thermodynamics for you. And you can tweak the theory around so that the output is the mean squared electron density fluctuations. And those are what cause the radar scatter and control its power spectrum. And so, it sounds really simple now, but it took us a while to figure this out, to say the least. And also then, what you wind up with is you have to do some kind of nasty numerical integrals. But fortunately, Cambridge had then had what now is an incredibly primitive computer, but they had it, and they had a programmer who knew how to program it, and so to do the numerical integrals, and the result is not a Gaussian. You get a double hump spectrum, and the Doppler shifts are characteristic of the ion velocities. And you can also think of the spectrum as resulting from heavily damped up and down going ion acoustic waves. That's another physical way to think about it. You can also do this whole thing that many other people did from a so-called dress particle point of view. You have a moving ion that attracts a cloud of electrons around it, and the cloud has a radius of about a Debye length, and so the slow-moving ions contain, in effect, about half an electron and a deficiency of about half an ion, and that's saying it all very crudely. But anyway, you can do it from that point of view, and you get the same result. And this is more about that. I guess I won't go into that, but there's more details about the clouds and ways to think about them. So depending on how the effective cross-section, so to speak, of this ion plus a cloud depends on how fast the ion is going, which is what winds up giving you the double humped spectrum. And this whole picture doesn't tell you anything about plasma lines, but because they involve a sharp resonance. But both theories can account for that. Both approaches can account for that. So the bottom line is only if the lambda radar over 4 pi is much smaller than the Debye length does the Gordon theory really apply. And this inequality is very seldom met, only at very high altitudes and high temperatures and low densities and so on. And if TE equals TI, which is not always true, that the total scattering cross-section is 1/2 the value predicted Gordon, but the power spectrum is much narrower, so the signal is easier to detect. And I want to emphasize here that it's the theory predicts the statistical properties of the signal, not the signal itself. So there's no useful information in a single echo. And some years ago, I received a couple of Russian papers to review that were talking about single pulse incoherent scatter and how variable the ionosphere was. And you got different results with each pulse. You know, it really varied a lot. And I rejected that paper, and that was not heard of again. I said, you know, read a little bit about statistics or something. You know? And so, but anyway, I mean, it was, and these were probably pretty good scientists, but they didn't know much about, they didn't have much background in this. And so anyway, there's the spectrum that Gordon predicted, and here's this sort of correct spectrum for TE equals TI and so on. And so this is and I forget what frequency, this is for 400 megahertz. And so here the spectrum is like a reasonable fraction of a megahertz wide, and here it's a few kilohertz wide. So that doesn't sound quite right, but anyway, it's way narrower and has this double humped shape. So I want to insert here, because this doesn't get said very often, the complete success of the linear theory in explaining all the incoherent scatter spectral observations that have been made to date, and everything you can imagine, provides what's probably by far the best quantitative and detailed test of kinetic plasma theory. I mean, it's just, into 3 significant figures. The incoherent scatter results agree with the predictions of plasma theory, and I don't think there's no other plasma experiment that I know of that you can test that way. But in order to show this, we had to figure out how to accurately measure the spectrum and the power, and this is not so easy. I mean, I think we do it now all the time, but it's not. So the spectral shape depends on the temperatures, it turns out, with the right theory, and the ion composition, the drift velocities, and various other parameters of the ionosphere. So it's important to measure this spectrum in detail and as accurately as possible, and this is not easy to do. So it's easy to measure the Doppler shift of a radar echo from a single hard target. You just have a plane going there. That's easy. But what about a diffuse distributed target with a broad range of velocities? Well, then it's not so easy. And you have to deal with problems of range and or frequency aliasing if you use a pulsed radar. which is the usual case. And you have to worry about spectral convolutions if you're transmitting pulses, and so you're convolving the natural spectrum, the plasma spectrum, with whatever spectrum you transmit. So that complicates your life considerably. And so, again, on the range aliasing thing, to avoid range aliasing, in other words, the ionosphere is a really extended target, which makes life difficult. To avoid range aliasing, you want to send your pulses far apart. But in order to avoid frequency aliasing, you want to have your pulses close together. And in many targets, you can satisfy one criteria, but not both. And the ionosphere is such a target. If you can't deal with both problems at once, then the target's called overspread in the radar jargon, and the ionosphere is such a target. And so what do? Well, you're saved by two things. The power spectrum is it's well known. The power spectrum is the Fourier transform of the autocorrelation function, the ACF. And second, and also and extremely important, the echoes from two disjoint volumes of plasma are statistically independent, and that's crucial. We'll get back to that. But I'll just look at first we'll look at the simpler case where you have a bistatic radar. If you have a bistatic radar, you're transmitting here, you're receiving there, and the geometry of the two beams determines where the scattering is coming from. So you could transmit a CW signal, a single frequency, and then what you'd get back here would be just the natural spectrum of the plasma. It would contain all the Doppler shifts put in by the plasma, and the altitude resolution would be determined by the geometry of the crossing beams. And the French actually did this in the early days. The French had a system where they had a transmitter in one place, and they had a big radio astronomy antenna in another place, and they did just this. They had these crossing beams. But you can only look at one altitude at a time. It's very tedious to do this. And so they got very nice spectra as a result, but you couldn't do much more in ionospheric diagnostics. But now, so what you do, and what we did at Hikamarka in particular, was shown by this double pulse technique. If you transmit a pulse, and a little while later you transmit another pulse, and then you receive, and the same separation you receive a second time. Now, so on this one you receive echoes from that, and with this reception you receive echoes from there and there. But these volumes are completely separate. They're completely disjoint. So the signal in this volume and this volume are totally uncorrelated. So if you now correlate the two received signals, the only place that things will add up is this volume. So you can get your information from the volume described by those two triangles, and these other stuff will average out. That will all average. Those contributions from those two things will average to zero, and so that's what you do. And so you get resolution in both altitude and time lag, and the time lag is equivalent to frequency basically when you do the Fourier inversion. And so you get one lag for this at all altitudes, and then you vary the lag cyclically to build up the full ACF. And of course you receive from many range bins, so you get all altitudes at once for this particular lag, and then do the same thing for another lag, and so on. And you can extend this. You could transmit 4 pulses, and you can convince yourself that only the echoes from these 4 will be correlated, and all these will average to 0, and so on. You can go with even more lags if you want. And then you can use cyclic or random codes. This was pioneered by the Finnish group at ISCAT, and Mike Sulzer has done a lot with this. You can vary these numbers either cyclically in a cleverly chosen way, or just randomly, and gradually all the stuff from the gray areas will all average to 0, and all that will survive are the signals from the black areas. And you can extend that to pulse compression. If you transmit a code, this would be like a phase code, the 180-degree phase flips. if you transmitted plus, 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 minus, plus, and you receive here and add all these up, you can see that you'll only at this one particular altitude will everything add up in phase, and the other ones will have either no contribution or a small contribution. So the upshot is, if you do this, you can transmit a signal that's so-called 5 bauds long, and what you'll get out is an echo that's only 1 baud long. So you can do pulse compression, which is a clever technique. But to do all this, you've got to have the right equipment. You've got to be able to make these phase codes, and you've got to be able to receive them, and you've got to be able to put them all together. And so you have to have a digital device. And well, there were no digital devices that were remotely up to this in the early 60s, but I think it must have been Ken Bowles that realized that this is what you had to do, and he talked to people in Boulder electronics labs, and they built up this device called the Correlator. But it was also a radar controller, so it transmitted the right kind of pulses, and then it had all kinds of gates and flip-flops and counters and stuff, and put them all back together again. And this device was absolutely crucial for Higa Markham, and it was quite, well, it was amazingly powerful and versatile, given that nobody had ever done this before. And then the second thing that came along in late 1963 was a Packard Bell. It was our first computer. It was the first computer in Peru, and it was, an incredibly primitive computer. And the memory was made up of 16 acoustic delay lines. So you put in a pulse at one end, and then it goes around the line in a spiral, and then you pick it off the other end and feed it back in. Okay, thanks. And anyway, so but the interesting thing to note is, first of all, the 16 delay lines each had 256 words, so this is like 4,000 words. This is the whole memory. You got to have your entire program in there and a place to put the data and all this kind of stuff. So that was the whole thing. And there was the added fact that this acoustic delay line, it traveled at the speed of sound, and the speed of sound depends on temperature, and the Higa area for this was not air conditioned. So the speed of sound would vary, and from line to line. So often you had to go in there and, quote, tune up the computer. You had to go in there with your oscilloscope and get all the lines adjusted so that they had the same delay, which was a challenge, especially when the program starts out working and it doesn't work, and then so you go back and retune your computer. So anyway, the radar controller could do all kinds of nice things. It was really 2 separate radar controllers, so you could run one for one pulse and then one for the second pulse, and you could generate different polarizations. You could do cross correlations, and thumb wheels control the timing, and each program step could do a lot of things together, so it was much more powerful than you think, with a total of 16 program steps, or 2 times 8 program steps. There it is. That's the Correlator. About more or less 5 racks of stuff, and these are thumb wheels or counters and things that control the length of the pulses and the separation of the pulses. And here's this thing called a plug board, or a patch panel, that put it all together. And there's an example of a pretty simple program. So you had 1,024 holes here, another 1,024 holes there. So you had 1,024 potential wires to hook one to the other. And and the complicated programs, and I did a lot of this. I mean, it could be maddening to do this and debug the program, but I was one of the ones that did a lot of this, and we had a couple of boards in which every single hole was filled, and then we needed to do a few more things. So people would put on strap on a piece of aluminum on the top and build a little circuit, and maybe a couple of switches, and so they were sort of outrigger kind of things that added on to this. So then you could do a couple of things at once. But anyway, and also you had to cope with the fact that most of the wires we had were gold-plated to reduce the contact resistance, but after a while we didn't have quite enough of those. So you had to go with aluminum-plated tips, and sometimes they didn't work because the contact resistance was too high. So you'd slam the board in and out 4 or 5 times when it wasn't working, and then it would usually start to work, and then you could carry on. So it was an interesting time. And here's the PB250. Again, it had this was the memory, and it had 12 kilobytes. And well, it's an interesting story which I don't really have time for. But the upshot was this thing. The computer arrived, and Ken Bowles was very eager to get it running right away. We plug it in, it didn't work. Nothing worked. So he gets out the circuit diagrams and starts tracing through, and he finds that there's a lot of stray pulses in it. So he puts in 20 or 30 diodes to clip off the pulses of these stray pulses in key places, and lo and behold, it worked. And then he thought, well, as long as I'm having so much success so far, I've got one more thing to do, because the computer was built to always start, the program always started at location 0000. And we said, that's inconvenient. So he drilled a few holes in the computer. And, you know, people don't drill holes in computers, but he drilled a bunch of holes. And he put in 4 switches so you could select, it could start at position 000 at any one of the 16 lines rather than just one. And that was a great help because you could start things. And so the technician arrived about a week later, and it was who was going to install it. And so the technician says, yeah, it's up and running, it's working fine. He said, it's up and running. It can't be up and running. You have to put in all these diodes. And he said, yeah, I figured that out. And so the technician was quite impressed anyway. He must have given us a few other tips, but basically his job was all done. And well, anyway, and these were, well, anyway, programming this thing was maddening because you had to, it was like a magnetic drum. You had to ask the right question at the right time. And again, the tuning and so on. But so it took a long time to debug the programs. But anyway, it was a huge step forward because at least it was a computer and you could do things. Okay, now I'll show you just a few early Picammarca experiments. This is took the first Venus echo and at 50 megahertz, and this was no big deal in a sense, but because Arecibo had already done it. I mean, Arecibo was much more powerful for this, but we did it just to see if we could do it, and you know, lo and behold, it worked. And this was interesting. There was an experiment, a starfish experiment out in the Pacific, where they exploded an atomic, a nuclear bomb at like 400 kilometers, injecting vast numbers of MeV electrons, and they precessed around, and so the background noise went up by about a factor of 3 or 4 there when it went off, and it stayed up there for measurably for many months. And this was the time history at Picammarca, and if you and since the time, this was precessing around about 90 degrees of longitude, and so the fastest electrons got first, and then so on and so forth. So if you invert this, I mean, I've figured out that you take the public spectrum and you invert it, and lo and behold, it looks exactly like that. And so the first time around, everything is pretty well bunched up, but the second time around, everything is spread out because they've been going around at different velocities. And here are some high-altitude profiles, and you notice that the number up there, that's 6,000, 8,000, 10,000 kilometers. So we did some really high profile measurements in those days, and here's where I think the only time we ever ran for like 5 straight days. And these contours are it's electron density this way, and these are constant altitude. So we take many of those profiles and reduce it this way. So these are going up to 7,000, 8,000 kilometers, and so we ran for a whole day. That was really hard on the transmitter and the whole system, but we only did it once, I think. And and then there was a total solar eclipse predicted for 1966, and so everybody was supposed to get there very early, and I say, little did we know. And so a major fire broke out a couple of hours before the time of the eclipse, which was not good. And so we had everybody there in case something went wrong. So there was a Peruvian electrician who had installed all the cables in the tunnel, kind of remembered which was which. And in spite of all the smoke, he got the fire put out pretty quickly. And we started the observations more on time. There's the fire. Here's one sunrise, and then it goes away. And then here's the second sunrise here. And in between here, well, these are temperature measurements, and it can't go through. But anyway, there were high temperatures right in this gap here. The electron temperatures were very high, so it was a very cool experiment, actually. And I don't know if it's ever been fully analyzed, but anyway. And then there was the ion gyro resonance. One reason for building the radar in Peru was because you could look perpendicular to B, and the thought was you could measure the ion gyro period, and it would act like a mass spectrometer. And it didn't work, but then I eventually figured out that, well, it can't work for O+ ions when you think about the perturbations on the orbit, but it should work for H+ ions. And so we did that, and here's how it comes out. And this is at 1 gyro period, 2 gyro periods, 3 gyro periods, and the X's and things are the data, and the solid line is a theory that came out of Ron Woodman's thesis. And I'm trying to get Marco Mia and Erhan Kudeki to do their new code for taking into account Coulomb collisions and run it on this and see how it tests out against that. But that was a one-shot plasma experiment. We did it only just to see if we could do it, and we did finally do it. So here's a bunch of pictures. I'll give you a whole bunch of pictures really quickly. Here's a photo from the air taken before anything was built, showing these what turn out to be flash flood paths, and you see little bushes growing. So if you give these bushes a drink every 3 or 4 years, they stay alive. And here is the road out to the observatory, the early road, and this is a huge Inca ruin here. It supposedly had about 50,000 inhabitants at one point. And here's a farm. Maybe bring the lights down a little bit more if we can. Something like that. See the pictures. Yeah, that's good. And here's looking at the site before anything was done. Here are some people doing some preliminary surveying in '59. And here's the dipole array. Here was a test string of dipoles to see how this dipole connection would work. Here are all the 9,000 posts before they got all in well, some of them have been done, but some of them not. And here's more work on the details. This is the last dipole, the golden dipole, which was put in, and that turned out to be a mistake because it got stolen 3 or 4 times. And so we finally replaced it with just a plain old ordinary aluminum one. And anyway, and there's showing the connections, and you get transmission lines coming up here, and they go up to these things, and they feed into that. And this is the connection there. So there's an inner conductor and an outer conductor, and the outer conductor is acting like the antenna, and the inner conductor makes it a transmission line. And so you switch phase every dipole, and it works surprisingly well. And there's a so-called switch yard where you change the length of these pipes to change phases and things. And there it is in 1962. And transfer. Here's an 80-ton transformer going over this bridge across the River Riamac. And everybody was really nervous about it. Nobody had any idea whether the bridge would hold or not. There was no way to find out. So there was one driver in here. Everybody else got off the bridge and off the thing. And he crept over this bridge, and it worked. But it was a little hair-raising. Here's a bunch of capacitors. Not too many of them actually were used in the final analysis. Here's a spark gap for discharging the whole power supply in less than a microsecond to avoid burning up the final tube. Oh, that's, well, okay, I already showed that one. Here's an actual WICO going down here, and a flash flood. these are pretty good sized boulder, and they move in this thing. And as I say, sometimes commuting was a little difficult because there's the road, and so you got to get across that road to get home. And there was a long story where once this was wiped out for a couple of days, and they had to, the only way to communicate was send a message to Boulder via two-way radio, and Boulder made a telephone call to the State Department. The State Department called the American Embassy in Peru, and the American Embassy got the word to all the families wondering where everybody was, that everything was okay. So it was communications have improved since then. Here's the bridge over the river there, and you can see the water is trying to get around behind the bridge right there, and it's right up to the edge, but the bridge survived. And here are a bunch of guys on that bridge, and some of you may recognize some of them. This is Ron Woodman, who was very involved in Hicamarca, and is still the director of the Peruvian Geophysical Institute. This is Bella Fair, not Jules Fair. This is me. This is Ben Balsley, and Ben Balsley was the one responsible for what's known as the Julia system, which is running Hicamarca on low power, but using all the transmitters, and so you can run it remotely, and it's a very useful system. Here was the first well, and there are stories about that well, but I'll defer those. I'll tell people about that some other time. There's a protective dam to keep those flash floods from destroying the antenna, but you notice there's some antennas outside the dam, and you're just gambling that they'll survive long enough to be useful, and sometimes they're not so useful. I mean, here's the flash flood going through that stuff, and most of had to redo that. Here is a picture of the first ISEA, the first International Symposium on Equatorial Aeronomy, and here is Sidney Chapman, who was mentioned in the talk a couple of days ago about aeronomy, and so that's Sidney Chapman, who was the grand old man of magnetospheric and ionospheric sciences in those days. And that's Ken Bowles, that's me, that's Ron Woodman, and here's Alberto Giesecke, who was the head of the Peruvian Geophysical Institute when we were there, and is still alive at the age of 92 or 93, I think. And anyway, that's a kind of interesting historical picture. And here are some early Arecibo photos, and there's Bill Gordon, and there's Tom Gold, and there's Henry Booker. And, well, this is Bill Sears, who had things to do with the sighting, and that's Ben Nichols, who was in electrical engineering in those days. And there's the spot where Arecibo is, and that's a nice picture showing the karst formations. And here's the Arecibo site before anything was built in it, and there's the tobacco farm down there. And here things are in 1961 and 62, where the triangular platform had been built, and there's a platform being raised, and raised some more, and still going up. And let's see, and there were 9,000 cubic yards of concrete in the three towers. And there's things being put together more in 1963, somebody on the catwalk, people putting on the surface. There's the surface when it's already on. The inauguration in 63, the first upgrade in where they changed the mesh to solid aluminum panels, which improved the accuracy a lot and made it work at higher frequencies. There's the panel number 38,778 being put in. Then the next upgrade was to add this Gregorian feed to everything, and then this was the thing starting to be raised, and it's called sort of the Starship Enterprise, and so there it is coming out of the mist, kind of a neat picture, continuing to go up, continuing to go up. I like that picture too, Arecibo by night, and there's another picture. Here's from GoldenEye, there's James Bond and a friend running around the antenna, and there's another person involved. That was Jodie Foster in the movie Contact. And, then an important question, yes, why is this dish 1,000 feet? And that was what Gordon had first suggested, but it was quickly shown that you didn't need a 1,000 foot to get the the sensitivity was much improved by the fact that the signal bandwidths were smaller. So you could reduce the signal bandwidths and then improve the radar sensitivity. But there was never any discussion that has, at least not in anything written down, of reducing the size of the dish to save money. And the original mistake turned out to be very fortuitous because, in fact, built the 1,000-foot thing, even though from an ionospheric point of view, it was no longer justified. But all the interested parties, especially including the military, realized that there were lots of other things you could do with a huge, reasonably steerable dish, and so they were unwilling to give up this option. And the military was willing to pump in serious amounts of money, and so everything went forward. And again, that Bill's quote comes up there. And so looking to the future, last few slides here. For Hikamarka, we can do more elaborate interferometry using various antenna modules, and I had a slide for that, but I didn't get it in. And continued use of the Julia mode. The Julia mode was attributed to was originated by Ben Balsley, and that's a mode in which you can use the whole antenna, but much less power. And there are lots of things you can measure that are interesting in that mode. It doesn't get you incoherent scatter, but it gets you drift velocities and various other things. And electronic beam steering is coming along. I'm not sure when but a lot of the things have been tested, so when that comes along, you can change the antenna position. Instead of hours, you can change it in seconds or maybe even milliseconds, depending on how the electronics is done. But now it takes pretty much a minimum of 2 hours to change all the cables to change a pointing position. And there has been talk from time to time of adding a wave heating facility, which would be a neat thing because the physics are different when you're pointing perpendicular to B and on long B. And although there's no serious proposal for that yet, but people have been thinking about it. And anyway, you can do lots of things. Hikamarka is very versatile, as anyone who's ever been there knows. And for Arecibo, well, there's a new heating facility coming, and even though it gets postponed a year every year, the hope is that won't keep happening. We'll get that pretty soon. And as far as I'm concerned, one thing that Arecibo is by far the best place to look at near-Earth asteroids, dangerous asteroids, and so that will fund them forever, I would think. And it would be nice to do more efforts on the plasma physics of the gyro lines and related topics like that. And new ISRs, well, you heard a lot about that yesterday, I guess it was, talking about relocating one or more of the A-misers, maybe in Ethiopia, maybe at HARP, and who knows. It would be nice to add a full A-miser to Hikamarka someday, because you need to have 2 frequencies. And if you do move one to Ethiopia, it would be nice to add a 50 megahertz array to Ethiopia, because you can do lots of things with instabilities at VHF frequencies, not the UHF. And there are many other options for A-misers. And then, as far as new scientists are concerned, there's a big legacy of students trained at Hikamarka and Arecibo, especially for Latin America. And I'd like to, if we could turn the lights up, everybody who's gotten a PhD related to, if everybody got a PhD related to Hikamarka or worked at Hikamarka or Arecibo, if they would stand up, that would be interesting. So anybody who's gotten a PhD that is involved in Hikamarka, Arecibo, I guess we can't count the people standing around against the wall. But anyway, there's quite a lot of people. And there's a lot more that aren't here. I should mention one in particular is Cesar Lagos, who came from Peru, but he did his PhD at Arecibo, and he's now a full professor at the University of Tromsø, which is about 400 kilometers north of the Arctic Circle, which seems like a strange place for a Peruvian to go. But anyway, he enjoys it there. And so anyway, a lot of really good science on both the experimental and theoretical side was done very rapidly in the first decade and of almost incoherent scatter, using very primitive tools by modern standards. And so, harking back to the talk on setting goals and risking things. Basically, two small groups of young U.S. gringo engineers had a lot of fun solving an impressive string of problems. I know I did. I mean, with that, we had a great time, and we worked hard, but we spent many long nights saying, you know, why the hell doesn't this particular experiment work? And eventually somebody would come up with an explanation. But anyway, their pioneering work led to the network of ISRs that are now operating with more to come, and good science is still being done and will continue to be done at Hikamarka, and so that's it. Sorry I ran over, but.